custom models are an essential part of zfit. As mentioned, zfit is not designed to ever provide all the models that can be used, but rather provide a standard one and make it easy enough that additional models can be implemented. So this is like a core feasibility that this is not too hard and kind of well designed. There are, let's say, two levels what you can do, how to implement PDF. And again, this is always just giving you a little bit more or less control of things. The easiest one to inherit from is the set PDF, which is really just a very, very simple version to implement something. What we do here is to implement a second order polynomial. We just inherit from this PDF. And all that basically does as well is it also cares about the init for you. It's really just the most simple version you can do. And what you need to do is just override this unnormalized PDF method with a leading underscore. It's a private method. This won't be called directly. You get in the X, which is the data that is unstacked. You can retrieve the parameters, and you can just implement anything in here using TensorFlow. Or even the set, which is, as we see here, from zfit import set. Set contains some functionality from TensorFlow as well, and just takes care of type, d-type casting, and so on. So if a function is there, you can use it, but you can use TensorFlow as well. It's just calling TensorFlow behind the scenes, so it's the same in a sense. With this simple PDF, we can just, with this definition, we can just create our PDF, get an observable parameter, and one thing here, if you want to have a constant parameter for a PDF, you also just can give in Python integer. This is very uncomplicated. And we can use the full functionality of our model, meaning we can integrate, we can sample, or we can use the PDF. As you've seen as well, this unnormalized PDF is not, so what we see here is the result of numerical operations. We didn't define an integral, we didn't take care of normalization. zfit itself automatically normalizes to the right range, tries to find an analytic integral, I mean if there is some register, otherwise it integrates numerically. Same goes for sampling. If there's an analytic sampling available, it uses that. If not, it goes for some accept reject algorithm. What we can do to extend our model is to define an integral. And maybe this looks a little bit too overwhelming for an integral, but it's just straightforward code. There are many examples around how you just define it. It's just doing some bureaucracy, let's say, which is just because with this way you can implement arbitrary complicated integrals or anything. But in the end, it's just nice to have this, define a CDF and then say, okay, my integral is the CDF of the upper value and the lower value, and that's it. I just added a print statement so we see if this function is really called. Then we can also say over which limits actually this integral is valid, so over which axis of the PDF. We don't know the observable yet, so we basically say the axis of the PDF is a zeroth axis, it's just one dimensional, and we specify the limits here. You can usually just copy paste that and fill out the blankets there, and then we can register it. And if we create a new PDF and use the same things again, we'll see a few times that we get the integral called, because now it used the analytic integral inside. As I mentioned, the deceptive PDF is slightly simpler. We will see a little bit later on how to also overwrite the init, for example, and do stuff in there. But for the moment being, we can also just use that. And what we see here is an example that I mentioned of a B2K star LL decay, the angular analysis. So this is now a three-dimensional PDF. What we can say here, this is not mandatory, we can say the number of observables, and we can specify here again the names of the parameters that shall be used, meaning this looks exactly the same as before. We just get our parameters inside, we unstack it. Now we have 3 dimensions, meaning we will get a list back of our 3 variables. And then we just implement the thing taken just from paper of the definition, and we get our PDF defined. That's all we need to do to implement custom PDF. Now, what we didn't look at is how can we actually define a multidimensional space. because we have a three-dimensional data set, so we need a three-dimensional space definition. And the most simple way to do is to just create a one-dimensional space object and then just multiply them. There's also a function which says combined space if you want to use that instead of the multiplication operator. And then we get the angular obs, which has then 3 dimensions. So this is a three-dimensional space, which has three-dimensional limits and such. A note on managing parameters. Above, you have now 9 parameters around. And if you go to do that for different years, maybe, and many things, it can be a lot of parameters, 20, 30, 50, whatever fit we do. And there's not a lot of managing parameters in zfit because this is just usually done quite simple with some nice Python code, a dictionary comprehension with initial values. We create our parameters, and we can just instantiate here our Angular PDF. Now, what we get out here is, again, the same functionality. What I'm calling here is just a cell that does integrate, that samples, and that gets a probability. And as we see, all these things just work seamlessly. We got a full PDF now with this definition. We can't even create a product. Before we already had a sum, but we can also do a product. And the product is very well defined because we have an observable associated to each PDF, meaning if the observable overlaps, so if it's the same observable, it's going to be a product that is going to be in the same observable. So if we have a Gaussian times another Gaussian and they're both defined in observable 1, then we're going to have, again, a one-dimensional Gaussian afterwards. If, on the other hand, Gaussian 1 is defined in observable 1 and Gaussian 2 is defined in observable 2, we're going to have a two-dimensional observable afterwards. So remember that we defined our poly 2 before in a different observable. This Angular PDF is defined in 3 angles. This is defined in a different thing. Could be, for example, a mass PDF. We can just multiply the 2, or also explicitly, as here, use the product PDF if we want. And we get a 4-dimensional PDF. As we can see here, by looking at the observables, we see that the angular observables cos theta k, cos theta l, and phi. The poly observable is observable 1, and now we have our full PDF, and the observable of those is just this 4-dimensional thing. Now, what I'm having here is an explanation of what really happens inside. And the short thing is that you can gain always full control of a PDF by overriding not the public method, but the private method. So if you want to change how integrate works, you can just implement _integrate for yourself if you want. Meaning you can always take full charge of a PDF. If you override _PDF, _integrate, unnormalized PDF, sample, then zfit doesn't do a lot anymore for you. What it still does is it catches some automatic things and it does some input pre-processing. So always, if you want to take control, use the underscore and then the method name. So you really overriding _integrate and sample and stuff, that's quite advanced and usually not needed. But one use case that can be interesting is to override the PDF itself. So what we have here is now we don't iterate from zPDF anymore, but from base PDF. Base PDF just requires you to write the init as well, but the rest is all the same. We can do unnormalized PDF or anything. And this is, let's say, the normal way to do if you don't want to do it very simple. What we basically need to do in the init is to get the observables, because that's what we need. And we somehow need to say what are the parameters. We can name them as ever we want. We can get them in the init, we can get them in the interface here, but for example, we can call them superparam, and we don't have a superparam here. We can receive already a dictionary of parameters. It's completely up to us. All that we need to do in the super call is define observables and the parameters. A name is not needed, but usually nice. This is just a human readable name of our PDF. And we also can do any stuff in here that we want, pre-processing, whatever.
Sorry, Jonas. Jonas, sorry. There is a typo, isn't it?
What?
There is a typo, isn't it? It should be. Shouldn't it be instead of x data times param3 in the when you define probes?
Oh yes, there's a typo. Yeah, you're right. Exactly. Yes. Thanks a lot. Yeah. What I mean is yeah, no, you're completely right. Yeah. So before we override unnormalized PDF, and we could do this here as well. But if we want, we can also override underscore PDF. Before the PDF function, when it was called, it looked whether there is an underscore PDF defined. If not, it tries to fall back and take your unnormalized one and does the integration and all this stuff. This is what it should normally be. If you really want, you can take over control what PDF does. Meaning, now you get an additional argument, normalization range, because it tells you now how it should be normalized. This can be differently, and this is not something you should hard code in general. So you can now do this stuff inside here. And this is usually just to integrate over the function that you just defined over this normalization range. That's why I usually don't want to care about it, but you can if you like. And I want to emphasize here that in principle, you can also hack something now. If you say, okay, this is too complicated for me to define an integral in general, and I can't do this, can't I just have this function? Yeah, you can. If you override underscore PDF, then this is what is returned by PDF. Full stop. So if you want to hack something, have a different scaling, don't care about the normalization, just make it usable for a very special case, this is all doable. Of course, again, this is something where, zfit relieves control and lets you do all this stuff. You can mess up, of course, but it also means you're not restricted to anything. You can always gain control if you like. But again, it's not the normal case to do that. Now we looked at how to define shapes, and there is one last thing that can be relevant. It's to create composed PDFs. So far we didn't look at that. The only difference is that instead of a base PDF, we use a base functor, which again is also a base PDF. It just provides you with a very nice mixin already that takes automatically care of PDFs. So the assumption is if you use a base PDF, then this does not depend on other PDFs, but it depends on all the parameters that you specified here and nothing else. If you want that, you could use that parameter. There are ways around, but this is actually the assumption that goes in there. While a functor can depend on other PDFs. Meaning, if we're now creating the init, we need to additionally give the PDFs up there. We can also have some parameters. For example, the sum PDF, of course, needs to get the PDFs up and the fraction parameters, but we also don't have to give it. This is up to us whether it has some parameterization or not. And what we see here is we just, for demonstration purposes, a very simple thing, which just takes one simple PDF and then squares that. And here we again define the unnormalized PDF. But for example, this could be that maybe we already know that what we're doing, it's normalized. Like if you do a product of PDFs that are distinct observables, we know that the product of their PDF is going to be normalized as well. So we could directly overwrite the underscore PDF if we know it's normalized already. So what we're doing here is we just call the PDF function of this PDF and square it. Pretty simple. And I think you can imagine how to now build something like a sum or something more general. And again, all the functionality works straight out of the box. If you implement a function that you need for your own, which can be a specific physics function or something, make sure that if you want to improve it, you can just contribute that to zfit physics, where also core developers can help you with that, and where you can contribute it back to the community. This doesn't have to be perfectly implemented or something, and we're helping on that. But this way, it gets used by others find bugs as well, and you're giving something back to the community. As a last thing here is, as you've seen yesterday with TensorFlow, because so far we use TensorFlow inside all the time. Maybe you didn't even really notice because it all looks so natural. And this stuff doesn't even count TensorFlow, but these are all TensorFlow operations actually. So you've seen us before that the tutorial state was quite advanced, all this wild stuff. In practice, it's pretty easy to write TensorFlow. It's a little bit like NumPy. But what we can do as well, as mentioned yesterday, is that we don't just use the graph, which by the way, as a side note, this also is automatically handled, that if we create a loss, this thing is now compiled in a graph and so on, but we didn't even notice that. And if you just call PDF, it's not, so it's more efficient. This It's just some heuristics behind the scene. You can always change that, but as you've seen, everything works smoothly as we wanted, fast enough and everything. Now, as we've seen, we can mix this in principle with pure Python TensorFlow. We've seen that yesterday, and it would be a good combo. So the important thing here is knowing that this is TensorFlow means we cannot really put in Python dynamics in here. If we use the graph, as we've seen yesterday, this doesn't work. So we cannot put in an np.random call or something. Meaning, yeah, as seen yesterday, everything has to be TensorFlow. But there are two ways of using full Python dynamics. One is, as mentioned yesterday, I think Ilya asked the question, to use this tf.py function or set.py function, which means this allows to wrap any arbitrary Python code. So for the smaller function, this is very useful. What you basically do is we have our Python function here, and we got our input tensor. So this can now sit inside the unnormalized PDF method. And now if you want to get y and we want to get this evaluated, we specify that, where basically the function is this, the function to be called. Our tensor input is this, and the output type is going to be a float 64. So we can just run this code. And of course, this is now not in graph mode even, so this is trivial that it runs, but if this would be inside graph mode, this would also function exactly the same way. We get a warning here from zfit, and this is one of the things that it does. If you use an advanced feature, you can use them, like inference and so on, but it still warns you just to make sure that you're not, that you're aware that you're doing something which is unusual. And what it says is that now you're using the py function, but you didn't use any kind of numerical gradient, because the gradient that is used by default is the TensorFlow gradient. I mean, it depends on the minimizer, but you didn't switch that off. Meaning, if you're going to use this in a minimization process, you're going to fail with it because it's maybe tries to use a TensorFlow minimizer. What we can do this is by using the set autograph mode to false, meaning now zfit does not use the automatic gradient of TensorFlow anymore, but uses a numerical gradient. And then we can use this fully again. We can also use the internal minute gradient. This also works. It's even better, I think, than the numerical one provided by zfit. But anyway, we need to use the numerical one. What we can also do in addition is to change the other thing. Instead of doing this py function, which works nicely for smaller things, but it's still not the full Python dynamics that we promised yesterday with TensorFlow, is to change the graph mode. So switch it off. Meaning now zfit, even if you decorate it with function, by the way, there you should use the set.function because it does some stuff and so on. This is all switched off, meaning everything runs now eagerly like TensorFlow if you use this flag. Sure, I said yesterday, if you use Python code, you don't have the whole speed up of TensorFlow anymore. And to give an estimate, this is maybe a factor of, let's say, 5 to 10 slower. Depends a lot on what you do, but let's say I did some comparison, prop fit, row fit, set fit on a nice simultaneous fit, and compiled. It's on the same order. It's roughly like row fit, and if you run it in this mode, it's still faster actually than prop fit, but it's just a factor of 5 to 10 slower. It depends, of course, on what you do, and it's the cost, of course, to get the whole dynamicity. But now we can define this numpy Gaussian, meaning inside here, we just use numpy functionality. All we do is we convert it again to a tensor when we return it, because the rest is still TensorFlow, and this is a little bit nicer to do. And another thing we put in here that's quite tricky. If you really need to do this kind of PDF, you can, but maybe don't forget to put in this assert statement, which means we can now just execute this function if we're running eagerly. So if we're not using graph mode. Because remember, if we would use the graph mode with the above function, it would just run the first time very nicely, probably, but just remembers all the static things from NumPy and won't do anything again, any calculation. So this is going to be a problem, meaning if you put this in, it will just fail, which is nice. And now we can use this, and we can even compare it now to the built-in zfit Gaussian PDF and integrate over a certain range, and we see the integral values are basically the same. So we see we can, if we want to have the full Python dynamics, we still have it with zfit. So on one hand, zfit has this high speed of TensorFlow graphs, and on the other hand, it has Python dynamics if we want it.